All right, let's go ahead and get started here. Once again, thanks for being here on time. I know 8 o'clock is not most people's favorite hour, but you were here on time and I appreciate it. Homework number 3 is due on Thursday the 6th of September, and you can find the PDF for that on MU Online. As always, that assignment's due before class on that date, so you've got a week to solve that assignment. It's largely related to interest and compounding, the sort of things that we're going to be covering in class today and the ideas that got introduced in class on Tuesday. So you should definitely get an early start on that, though there may be a handful of ideas that we won't get to until Tuesday's class. Okay, so during the in-class exercise that we had, we did kind of a weird procedure on Tuesday. Where what we had was an annual series, and we were trying to find out what was the future equivalent of that annual series. And I encourage you to think about it in terms of moving the arrows. And when you move those arrows forward in time, they get bigger because the effective interest means that the overall amount of dollars is increasing. Remember, what we know is that those dollars aren't necessarily more valuable in the future. In fact, it's the opposite. Money in the future is less valuable than money now, if we're talking about the same amounts. But in this case, since this was like a loan repayment kind of a situation, in year 4, you're going to have to pay more than the sum of these 4 amounts because there's the interest that you have to account for. You know, the privilege of borrowing all this money is going to have to be repaid and then some in the 4th year. And so what we did was manual compounding. And there are ways to solve this on Excel. There are formulas that will allow us to find this. But one of the things we talked about in class was how to summarize what kind of a problem it is. You know, find blank given blank. And so what is this? This is find something given something. What is it? What's that? Over here. I heard something over here. Okay. Find the future given the annual. And so that means this is an F/A type problem. All right, it's important for you to remember how to summarize problems like this in terms of the unknown and the given, because when we solve this according to formulas or according to a table of pre-solved factors, you're going to have to be able to know that, that shorthand. All right, so let's talk about compound interest, which was what we were accounting for. In contrast to compound interest, simple interest is where you're only paying interest on the principal amount, but you're not paying interest on the interest. So here, the formula that's given for calculating the interest amount, if you have a simple interest loan, is it's the principal amount, the number of periods, and the interest rate per period. The only time you're likely to see a simple interest loan in your life is maybe if your parents are the ones who are loaning you the money. Anybody else is going to be too greedy to extend you the option of a simple interest loan. Every other financial institution, whether it's a bank or a credit union or the federal government, they're going to charge interest on top of the interest. And so that is going to be compound interest. But before we get to that, just really simply, the way that we can calculate the repayment amount after 3 years in the case of simple interest, if our principal is $100,000 and the number of periods n is 3 years, and then the simple interest rate I is 10% per year. Now, a word of warning, you're going to have to just be able to know when you should exchange a percentage for a decimal. And this is one of those cases. If you put the number 10 in for I, you're going to be shocked at the interest that you have to pay, but it should be 0.1. So the overall interest amount is going to be $30,000 if there's no compounding in this case. So then the total amount due would be the principal plus the interest amount at the end of the 3-year period, $130,000. So maybe you already have a sense for this. If compound interest is applied, in other words, if every year the bank is recalculating how much you owe, and then they're charging you the interest for the next year based on the previous year's total balance. So that's the definition of compound interest. Is in simple interest, every year they were just thinking, well, how much was the original amount we gave you? And then they charge you the interest amount based on that original first principal. But compound interest, at the end of every year there's a reckoning, and so they find out the total amount due, and then the interest is based on that total amount due. So if we switch and we have the same $100,000 example, but it's compound interest, do you think it's going to be the total due is more, less, or the same? More, yeah, absolutely. So let's look at the formula, then we'll look at the illustration of it. So the interest amount is based on the principal plus all of the accrued interest to date. So the interest amount changes from year to year, because at the end of the first year, the balance that you had due was only the amount that they originally gave you. But then as soon as that interest accumulates, suddenly you owe more. And then the interest is going to be based on that larger amount. Now there's a formula for how to calculate the interest in any particular time period. So the interest at a certain time is going to be the principal plus all of the previous accumulated interest until the previous time period. So this is saying the sum from j equals 1 to j equals t minus 1. J just means some year. So the interest from the first year, the interest from the second year, and so on. And the reason why up here above the summation symbol we have t minus 1 is it means you're only paying interest on the interest from the previous year. You don't have to pay interest on this year's interest amount because it hasn't accumulated yet. And so that entire quantity of the principal and all the previous year's interest is multiplied by the annual interest rate I. By the way, it's important for you to be able to understand the difference between big I and little I. In fact, later in the semester, there's going to be 3 other kinds of I. I with various subscripts. And so I guess our book is a great book, but it's not so good at finding creative variable labels for certain ideas because it's reusing I over and over again. So the capital I here is interest amount, and lowercase I is interest rate, where it's an amount per time that's being expressed. Okay, so we'll take a look at this formula and how it's applied in just a minute. Before we do, let's step through this illustration year by year. So this is that same $100,000 amount, that same 10% per year interest rate. But now, instead of simple interest, this time it's going to be compounded annually. So that means at the end of every annual period, we're going to do kind of like a reckoning, or sit down, do the books, find out what's the total amount due. So at the end of the first year, we see the interest amount is based on the original principal of $100,000, so the interest amount is $10,000, so the total amount is the principal plus interest from that period, $110,000. Easy enough. The second year, the interest amount is now based on the previous balance of 110. So this is what we did in class on Tuesday, except for on Tuesday we had the added difficulty of each year we were taking a little bit more from the bank. So there was some cumulative balance and then a new withdrawal. So in fact this is maybe even a little bit simpler than what we did on Tuesday. Because here, once we have the interest amount of $11,000, we combine that with the previous year's balance, and so this $110,000 was the T sub 1, the total due at the end of the first year. And so that's where $121,000 comes from. And every year that interest amount is getting a little bit bigger because you have to pay interest on the whole balance. Until you give that dollar back to the bank, they're going to continue to charge interest on however much you owe them. Okay? So at the end of 3 years, instead of the $130,000, which is what we saw in the simple interest illustration, this is $133,100. So that's the comparison of compounded versus simple. So that formula that I showed you on the previous slide, this year-by-year approach didn't utilize that formula. Let me show you a basic idea of how we can use that formula. All right, so the formula was I sub t is p plus the summation of j equals 1, j equals t minus 1, I sub j times I, the interest rate. Okay, so in our example, the principal amount is $100,000. The annual interest rate is 0.10. And what we want to do, let's find out what's the interest in the third year. So I sub t. I sub t is I sub 3. So in other words, we just want to find the interest amount in the third year. This won't be the total amount that's due. Okay, so the principal was $100,000 plus the summation of all the previous year's interest. So in the third year, remember, the first year's interest was $10,000. And then the second year's interest from that example we just saw was $11,000. Okay, so that's what this j equals 1 through j equals t minus 1. So t minus 1 is 2. So we're going year 1 and year 2 interest amounts are being combined. And so this was the year 1 interest, and this was the year 2 interest. And we're combining that with the p, and then we're multiplying the whole thing by 0.10. So if we do that calculation, it turns out that the interest for the third year is going to be $121,000 times 0.10. And that's why in the third year we had to pay $12,100. Okay, so now you've seen that formula at work for how to calculate the interest amount in a given year when compounding applies. Any questions about this? Exactly. Yep. Just a given year, how much interest is due for that year. Of course, it takes into account the principal and all the previous year's interest before that year. Now, as per usual, I'm recording this lecture, and so if I work through any of these examples or if I say something too quickly, you can go to the YouTube video and review that. But it's a poor substitute for actually being in class. And the reason why is it's so much easier to get distracted at home than it is to get in class, you know, where you've got people calling you and where there's more interesting videos off to the right-hand side of the screen. So, you know, if you're sick and hospitalized, watching the video is better than nothing, but I'm glad you're here and not just thinking, oh, I'll just watch the video and it'll be fine, because it won't. There were students last semester who thought it would be fine just watching the video, and it wasn't fine. So, all right, so Let's also talk about the difference between nominal interest and effective interest. This is another bit of terminology that we have to clarify. It's talked about in the book. Nominal interest, when we distinguish between the two, we call nominal interest R. And so it's when an interest is compounded more than annually. So it could be on a quarterly basis or on a monthly basis, but then we quote that nominal interest on an annual basis. So nominal, this word nominal, is when people use it when they're trying to make something sound smaller. Like I was in a hotel once, and they said, we'll deliver food to your room for a nominal fee. Oh, that's nothing, it's nominal. But like their delivery fee was $12.50 to like bring a bagel up from the basement, So it wasn't really nominal, but it was their way of saying, well, you should act like it doesn't matter, right? So nominal interest is they're trying to make the interest seem smaller than it is. They're not actually taking the effect of the compounding into account. So that's what nominal interest is. And so, for example, we could say that 4% per period is 16% per year if it's quarterly interest. Nominally, it's 16% per year, but not if you actually take into account the compounding. So the only way that 4% per period, per quarter period, the only way that 4% per quarter is 16% per year is if you ignore compounding. But the people who say, nominally it's 16%, I guess technically they're right. But in reality, if you have 4% interest per period and you take the effect of compounding into account, then the cumulative effective interest rate is going to be more than 16%. So effective interest is like for people who know a little better. So an effective interest person would say, well, if you bring a bagel up from the basement and it's a $2 bagel, but there's a $12 delivery fee, the effective cost of the bagel is $14. It's not a $2 bagel anymore if you take the overall effect of all the surcharges and the fees into account. There's a question similar to that on your homework for someone who's taking out a student loan, and there's insurance and there's an origination fee. And so in that question, you're kind of calculating what's the real interest rate when you take everything into account. So it's important to understand the difference between nominal and effective. Effective takes everything into account, the everything being compounding, whereas nominal is just kind of like the blinders-on view. And I made some changes to the wording here compared to the slides that you've maybe printed out. I tried to clarify it a bit better than I'd had on previous year's slides. There's also some commentary in the book. Any questions about these definitions? Let's look at an example to find out this 16% here. I say it's greater than 16%. How much greater? Let's crunch the numbers on that. Here's the formula that tells you how to find the effective annual interest rate when you have some nominal interest rate. Now remember, a nominal interest rate can be quoted on an annual basis, but depending on how many compounding periods there are, we also need to know what is the nominal rate per period. And that's why here we're dividing by m, which is the number of compounding periods per year. So in the case that we're going to work through, we're going to say there's 4 periods per year, and so m, which is the number of periods per year, will be 4, and r, which is that nominal interest rate, it'll be 16% or 0.16, but then the nominal interest rate per period will be 0.04. I think you'll see that illustration here in just a second when we put this formula to the test. So 16% nominal annual interest rate, compounded quarterly is what effective interest rate? All right, does everybody have that formula copied down? See if you can calculate what is the effective interest rate. I'll give you a head start, and then I'll start putting the solution up here on the whiteboard. But I'd like you to plug the numbers into your calculator. Of course, writing it down in your notes before you plug it into the calculator, that's a great idea too. and then we'll see if we're all on the same page. Okay, so first of all, some definitions here. If we assign the variables, then the nominal interest rate per year is 0.16, converting 16% to a decimal. And then the number of compounding periods per year, if it's quarterly, then there would be 4 of them. And so you'll see here we have 1.04, because what we've done is we've divided the 0.16, which is the overall nominal annual interest rate, dividing that by 4. So it's 0.04 is the interest per period on a nominal basis. Take it to the 4th power because there are 4 compounding periods in each year. And so 1.16986 minus 1. The reason why we're doing the minus 1 is to subtract out the principal, because we just want to know the interest rate in the end. And so it turns out to be 16.986% on an effective basis. So the effective interest would be slightly higher than the nominal interest rate would suggest. And you may think, well, that's not a very big difference, 16% versus 17%. But over several years, that difference would have huge effects, because the way compound interest works, especially when compound interest gets above 4 or 5%, it's shocking how much the amounts snowball over time. We'll do some examples later on in the semester where a single % difference can mean the difference between a company's bankruptcy and a company being wildly profitable. So it is something to keep track of, this difference between nominal and effective. Any questions? All right, so we have a in-class exercise we're going to work through today, in-class exercise number 4. And I don't have names on the top, but actually I am going to collect it after all. I'm going to give you some homework points for your efforts today and for being here today. And so you'll need to write your name at the top of the page, and then before you leave today, set it out on the chair on your way out. And actually, before you leave, some of you may finish this sooner than others, and you're welcome to go once you're finished, but don't go before I have a chance to look over what you did, and we'll compare it to my answers. So everyone who participates today can get full credit on this in-class exercise. So let me hand this out. No need for whispering. Remember, this is the time where you can collaborate together as loudly as you like. You can shout at each other for all I care during these in-class exercises. So we're not in church. Okay, let me interject with a brief lecture about precision. And I've already, in a couple of cases, told you this individually, but I think it's important that we talk about it as a class so we're all on the same page. The solution to the InClass exercise should be coming up for the first two problems on the screen there. So I think everybody was on the right track, maybe off by a couple of dollars or a couple of cents, but your calculator will hold lots of digits of accuracy. You know, like when you calculate 1.04 to the 15th power, I wrote out 1.8009. That's what I wrote on the paper, but I didn't round that off in my calculator. I kept all of the digits because the final answer is going to be in the ballpark of 52,000. And if we want it to be accurate to the penny, then that means there's how many significant figures? There's 1, 2, 3, 4, 5, 6, 7. So 7 significant figures. That means that I should have at least 7 figures for that ratio, F to P. And so rather than worry about how many can I acceptably round off to, I may write some abbreviated version of that number on the paper, but in the calculator have the whole thing. And that way your answer will be correct to the nearest penny. All right, so that's just the one thing I wanted to say about rounding off is don't round off to the very end, and then you can round off to the nearest penny. Otherwise, just keep all of those digits of accuracy in your calculator. All right, on problem 3, there's 2 ways to do it. The first way is to, for that one that's compounding monthly. All right, yeah, plan 2. Okay, one of the ways to solve for the plan 2 amount is to convert this annual interest, this is a nominal, convert from the nominal amount and find the effective amount. So you could do that using the formula that is here on the whiteboard. Find the effective amount, and then the normal compounding way, n would be 10, since there's 10 years. Or the second approach to finding the plan 2 amount is take this annual interest and find out how much interest is that per month, since it's the monthly compounding period. So that would be 0.0725 divided by 12. That's your interest rate per period. And once you know that interest rate per period, then n would be 120. There would be 120 periods instead of 10 if we were going to take that approach of just accounting for the interest on a monthly basis. Either approach will give you the same right answer. So you can find the effective annual rate and then compound it 10 times, or you can find the monthly rate and compound it 120 times. Okay, so as I mentioned, there's 2 ways to solve problem 3. On the projector here, on the TV, I'm showing you one of the methods. Okay, plan 1 is easy because on plan 1, we've got the annual interest. It's compounded annually, so n is 10 since there's 10 years. So you can see what we've got is some factor, and this factor is the ratio of the future to the present. So if I multiply that ratio by the present, it gives me the future. In other words, the factor is F to P. So if I move the P over to the right-hand side of the expression, then I'm solving for F. So we find some factor, multiply it by P, and we find the future amount is 257,628 and change. Now plan 2, what I've got on the screen here is I said, let's just say how many periods there are. If they're monthly periods, there's 120 months in 10 years. And the interest rate per period is this nominal annual interest rate divided by 12, since there are 12 months per year. And so I now becomes much smaller than it looked like before. You know, before it was 7.25% per year, but I found this interest rate per period and take it to the power of 120. So I get a different factor multiplied by the present amount it turns out to be $257,529.02. Now on the whiteboard here, I've solved it according to the approach, what if you find the effective annual interest rate instead of the nominal annual interest rate. So if we go through this formula where it's 1 plus r divided by m to the m power minus 1, we find the effective annual interest rate, and then compound that 10 times since there are 10 years in this question, and we'd get the same final answer of $257,529. And of course, the difference between those two amounts is about $99.92. So plan 1 is better because it has the higher interest rate, even though it's only compounding annually. So if you're trying to weigh apples and oranges, like if you're comparing things that are dissimilar, you have to take them to the same basis to know which one is better. If this other bank was saying, sure, we don't pay as much on an annual basis, but we compound more frequently, so you're better off. You can't just take that claim at face value. You'd have to put it to the test and find out how much extra money could you get going one place versus the other. All right, so you've got some more questions on the back side of the paper, and then also this bonus question I'd like you to do. Once you solve 4 and 5, this is bonus question number 6. The computer thinks it's smarter than me. There we go. All right, so that's question number 6. This cash flow diagram should look familiar. They say history doesn't repeat itself, but it does rhyme. Let me pause the recording. Make sure we're all on the same page with stuff here. All right, so if we've got 24% per year, and that's maybe a typical credit card rate that would be quoted. In fact, credit card rates are sometimes even higher than that. But what this shows is that if it's compounded quarterly, the effective is only going to be 26.25%, and the more frequently it's compounded, the higher that effective interest rate goes. And there's even something called continuous compounding, where they're compounding every second the interest rather than on a daily basis, although the incremental amount is getting smaller and smaller. So the difference between continuous compounding and daily compounding is pretty minor, but they'll squeeze every penny that they can. So any questions on number 4? All right. Translating the statement into a cash flow diagram, this is what it should look like. You need to, just as a couple of the important stuff that should be on there, you need to have the interest rate written someplace. Of course, it's a horizontal line with tick marks that are roughly equally spaced apart to represent the time. And we have cash inflow amounts. $247,000 is going to be coming in. There's the salvage value of $95,000 in the year that the truck is sold. There's the annual fuel costs, and then a refurbishment expense in year 3. And then this dashed line means we don't know. That means we're solving for some amount. And what you're solving for is how much, how did I put it in the handout itself? How much can your uncle afford to spend? And so to make it all balance out, if you were going to solve for this, you'd be solving for the maximum amount your uncle can spend. Oh, did I write it wrong? Yeah, you're right. That's a misprint. It should be 55,000. Thanks for noticing that. So let me fix that right now so I don't forget. So that should be 55,000. So that's 55,000. Thank you. All right. All right, and then this last bonus question. Boy, before I moved on to the bonus question, are there Any other issues or questions you've got about 4 or 5? Okay, so on this last one, this is the same cash flow diagram that we had in class last time. And so there are simpler ways to solve this type of a problem than a year-by-year accounting and compounding of the interest. I gave you the formula there, F/A. And what an F/A operation does is it translates some amounts a certain number of years into the future. So we've got 1, 2, 3, 4. Okay, and 0, of course. So we've got all these 12,500s. When you do an F/A conversion, it moves all of these amounts to the last year that there was an annual series. You wish that it would move it all the way to year 4, but that's not how an F/A conversion works. An F/A conversion is going to move, however many you've got. In our case, there's 1, 2, 3, 4 annual payments. And so n equals 4. And the I in this problem, I is 0.05. And so if we solve for that, the F/A ratio, 1.05 to the power of 4 minus 1 divided by the 0.05, that means the factor is going to be 4.310125. That's the factor. And so here's this F that we're going to solve for. We had an A of 12,500. And so we can solve for F. It's the annual amount of 12,500 times that factor. 12,500 times 4.310125. And so that amount, if you put the numbers into the calculator, it turns out to be 53,876.56. Does anybody have their in-class exercise from Tuesday? Hopefully you're keeping a binder with all that paper in it. I put the holes in them each day because I'm hoping you'll hold on to these. There will be 30 of them through the semester, and it should be a really valuable resource for studying for the final and so on. The reason I ask, if you've got the one from last time, look through that chain of compoundings, and do you ever see that number someplace? Where is this number in that in-class exercise from Tuesday? Year 3, right. So it was at year 3 that we saw 53,876. And so then how do we find out the year 4 amount? We have to do one last operation. We would have to do find future given present, and the way that we can do that is it's just 1.05 times what this previous amount was. And so then if we had another 5% increase, because one more year of step from 3 to 4, so you take this 53,876 times 1.05, and then we get to the 56,750, which is the same 56,750, which is the overall future amount. 56,750 that we saw from class last time. So it all matches up. It's just this F/A operation is a little bit easier than going year by year and compounding. So we'll come back to this idea. If this feels foreign and unfamiliar so far, that's okay. We'll get to it. But I just wanted to give you kind of a sneak peek and an early taste of what we're going to be doing with these cash flow diagram translations. Okay, so before you head out, let's just take one more glance at these announcements. Homework 3, the PDF is posted on MU Online. You should get an early start on that. Please be sure to leave your in-class exercise for me so I can give you some homework points. I'll put those into the grade book, and then you can pick it up either outside my office this afternoon if you're eager to get the paper back, like as a help on your homework. Otherwise, I'll bring it to class on Tuesday. Have a good one.